Hello, everybody. So what we're going to be looking at today is section 4.5, the chain rule. And so here's what we're going to be doing. So we're going to state the chain rule for one or two independent variables. We're going to use tree diagrams to help us figure out what the formula should be. And also, that's a P there, we're going to perform implicit differentiation. So these are our three topics. And the reason we have to have a whole section on the chain rule is because we got functions of multiple variables now, and we don't know how the chain rule works in that scenario. You know the chain rule from Calculus 1, of course, but this is going to be different. All right, so let's go ahead and get started. This is a nice topic, not too hard. Homework should be reasonable. Sometimes I say that and it turns out that I'm lying, but we'll see. So recall the chain rule from Calculus 1 for a function of one variable. So if you take the derivative with respect to x of a function of x, you know what that looks like. It is f prime g of x. And then the chain rule part is you multiply by the derivative of what's inside, right? So that's your basic chain rule. You can also, write this a little bit, let's see, differently. You could say like this would be, I don't even know if I want to write this, but I think I will, and then maybe I'll erase it. But like this is the derivative of f with respect to g. This is like df dg. And g prime of x, that's the derivative of the inside function g. That's like dg dx. Now, nobody ever writes it this way, but you could think of it as being this, because this right here, this part is just the derivative of the outside function f. And this is just the derivative of the outside function f. And then here's the derivative of the g, and then this is just the derivative of the g. And you can't take the derivative of f with respect to x here, because if you could, then there wouldn't even need to be a chain rule in the first place, and so on. So, people don't write this, but, technically that's just the same thing. Okay, now let's see here. Now, I think I want to give you a formula, and then I want to do the tree thing before we talk too much about it. So here's a theorem. So this is going to be the chain rule for one independent variable. All right, so here's our scenario. Suppose you have the following. So z is a function of x and y. Okay, but then x and y are also functions. So this is the new thing. And x is a function of t, and also y is another function of t, like so. And what we want is the derivative of z with respect to t. So it is given by, and I'm going to write this in a second, but I just want to come up here and just say this. Right, we wrote this here in this form, but we could have said something like this. We could have said, like, y is a function of g, like that, and g is a function of x. So the g is a function of x, so you put the g in there. So f is really a function of x. But in order to find that derivative, you have to do this chain rule thing here. And so that's kind of the scenario that we've got going on here. We want the derivative of f with respect to t, but z is a function of x and y. So z is a function of x and y, and x and y are functions of t. Okay? And there's a formula for it. We'll write down the formula, and then we'll try to convince ourselves of why this is true. Will I prove that? Hold on a second. Yeah, absolutely not. We're not going to do the proof here. So here's the formula. So you want the derivative of z with respect to t. Now notice I'm using the notation for the derivative from Calculus 1, not using the partial derivative symbol. Because this isn't going to be a partial derivative, this is going to be just the derivative of z with respect to t, and it's made up of partial derivatives here. So dz dt is the partial of z with respect to x times partial of x with respect to t. Now that, actually, if you think about how I wrote this, right, think of this as being dz dx, dx dt. That actually looks just like this, right? Like df dg, dg dx, which is what you've got here for a chain rule. So that actually looks like the same sort of thing that we've seen before. But there's another partial, there's another part to this. So you could also take the partial of z with respect to y and then multiply by partial of y with respect to t, like that. And so it doesn't work this way, but like in your mind, you can convince yourself that this is correct, because if you see the delta x there and the delta x there and the delta y, you can think of this and this canceling out, and you could think of the y's canceling it out. And then what you've got here is like dz dt, which is what you want, and dz dt, which is what you want. So like both of these are really just ways to get you dz dt. And again, that's the same thing you've got going on here, where you could think of this as being like those canceling, and you would have df dx, which is of course what you were trying to calculate, was the derivative of f with respect to x. Okay, so again, this is like what you've seen before, but you can't cancel those, because like, this right here, partial with respect to x, is not like an item that can be separated from the z here, right? This is nothing on its own. It's part of the derivative. So you can't cancel them the way I drew it, but this is the formula that will calculate the thing that we want. Okay. Now, what else can I say about it? I think there's a little bit more to say. This is going to be no, that's fine. Okay. I'm skipping the proof, so I'm not going to prove this, because it uses something that I didn't go over from the previous section. So I'm skipping this proof. Also, it's a long proof. Okay. Now, if you're going to use this, you'll see that it's actually very simple to use. So these problems, I mean, I know what the problems are in the book. I don't know what the problems are in Newton, if I'm being honest. And, it's possible that they will kill you with what they have. But at least in principle, these are very simple problems. So calculate dz dt for each of the following. I'm just going to say for the following, because I'm only going to do one. All right, so I give you a z. Z is a function of x and y. It is 4x squared plus 3y squared. But then x is a function of t. X is sine t. And y is also a function of t. Y is cosine t. Okay, so do you see what's going on here? I mean, of course you do. this one's got an x and a y, but the x and the y both have t's, right? So that's the scenario where you need this chain rule, right? Z is a function of x and y, right? X and y are both functions of t. And if we go up here somewhere, I said that this is the chain rule for one independent variable. The independent variable is the variable that you can pick to be anything, and then the other things are calculated based on it. So in this case, right, if z depends on x and y depend on t, t is the only one that you get to pick, really. And so that is what we call the independent variable. The one independent variable is independent variable is t. Okay, so that's just kind of a comment. And then let's get going. So this is actually very simple to do because it's just you write out a few partial derivatives and then you just stick them together the way that the problem said to do, right? So one partial derivative that we need from this formula here, right? There's four of them. We need partial of z with respect to x, partial of z with respect to y, and then we need partial of x with respect to t and partial of y with respect to t. So we just calculate those, right? So you've got z is a function of x and y. We need both of its partials. So you need partial of z with respect to x. That's going to be easy. What's this derivative? It's going to be 8x, right? Very simple. We need the partial of z with respect to y. So we take this derivative with respect to y. That's going to be 6y. Also a simple partial. Then you need partial derivatives of each of these. But they're also simple functions. So we need the partial of x with respect to t. So the partial of x with respect to t, we just need the derivative of sine t. That's cosine t. And also we need the partial of y with respect to t, which is here. Partial of y with respect to t is the derivative of cosine t, which is negative sine t. So that was all the work. Well, I mean, most of the work. So then you just put it together. Maybe I'll just like steps here. So first thing we do is we compute these partial derivatives. Okay. After you have the partial derivatives, what you want to do is, write out your formula for dz dt. Which is not going to be hard, right? dz dt, you're just looking it up. It was partial z with respect to x, partial x with respect to t. Again, the way you get that right is by remembering that it looks like those dx's can cancel and leave you with dz dt. What it looks like. Plus partial of z with respect to y, partial of y with respect to t. And then you just fill in your stuff. So you have dz dt is dz dx, which is 8x, dx dt, which is cosine t, plus dz dy, which is 6y, plus dy dt, or sorry, times dy dt, which is negative sine t. So you end up just with simply 8x cosine t minus 6y sine t, like that. And that's your dz dt. Okay, now technically we've done the problem at this point. However, this is not like what you would want for a final answer. And the reason you wouldn't want this for a final answer is if you look at this, it looks a little weird, right? Dz dt. So we're saying that the variable is t, right? But then there's t's, but also x's and also y's. And we don't really like that. Okay, so we don't like having the answer with the x's and the t's and the y's. So I'll just note that we don't like writing it this way. With x and y and t all in there. What you can do is you can go back to the original function here, and you can say, well, x is actually sine t and y is actually cosine t. So you can just fill those in for the x and for the y, and then everything will be in terms of t. So that's usually what you have to do for like a last step on here. Again, it's super simple, but you just are supposed to do it. So let's see. We're going to replace x and t, nope, x and y, so that we have everything in terms of t. So again, pretty simple. You have dz dt equals 8x cosine t minus 6y sine t. I have no idea why Notability is like lagging right now. Haven't done anything. What do we know? We know that x is sine t and y is, what is it, cosine t, probably like that. So you just substitute that in. And so you have dz dt is actually 8x, but x is sine t. And then you have 6y, but y is cosine t. So you end up with that. And then you realize that these are actually like terms, right? Because this is sine t cos t, and this is sine t cos t. So you just have 8 of those minus 6 of those, and therefore you simply have 2 sine t cos t's. And that's actually what you would want to box for your answer, because that's just much simpler there. Now, let me just try to get rid of the lag here. I think that's better. What? Okay, well, I got to rewrite it. Hold on. 8 sine t cos t minus 6 cos t sine t, which is 2 sine t cos t. Okay. All right. So that's how we did that. And then just to convince yourself that this is, correct, and also just to show you that, technically you don't have to use this chain rule, you can actually do this derivative in another way. So you don't need to do this, but this is just, we'll just compute this with another method. We can. So we could have computed this without that chain rule formula. Okay, so if we go back to the beginning here, we have, wherever it is, right here. Gonna duplicate that. I think I lost a variable or a number here. So we got this 2 here. So we could have calculated this derivative a different way. You could have actually substitute what x and y are into the z equation. So you could sub in x equals sine t and y equals cos t into the z equation. And like if I had asked you to calculate this derivative without telling you how to do it, that's how some of you would have tried to do it. Okay, so you get z equals, you have 4x squared, but x is sine t. So, sine squared t, plus 3y squared, but y is cosine t. So you have cosine squared t, like that. And then you could actually just calculate the derivative directly. You could actually just find dz dt. Right? And you don't need any complicated calculus 3 rules. You're just going to take this derivative with respect to t. So dz dt is 4. And then for this is sine t squared, right? You could write it this way. And you could also do the same thing here for the cosine. So you have to do the chain rule. So that would have been 2 sine t to the first power times the derivative of what's inside, which is cos t. And then for the other one, you've got 3. And then you take the derivative of cos t squared, which would be 2 cos t, and then times the derivative of what's inside, which is negative sine t. And you end up with 8 sine t cosine t minus 6 sine t cosine t, which is 2 sine t cosine t. So you end up with, of course, the same, you end up with the same answer, of course, no matter which way you solve it there. Okay, so that's not, anything fancy. It's just, hopefully this will, help reinforce the idea that this formula that I gave you up here is actually the way to go. Make that work out. Now, you could say like, well, what I just did there to calculate that derivative seems easier than how I did calculate it. And maybe you're right, but the thing about this form is that I had to use the chain rule like here twice. Whereas in this version, even though it was called the chain rule, I didn't actually use like the old school chain rule at all, right? I had 4 simple derivatives and I just put them together. I never had to think about like a chain rule or anything really when I was doing it. And some problems are going to be easier with one method or the other method, but it's called, this section is called the chain rule, so they expect you to do the first method and not what I just did. That was just kind of just to convince you that this was an alternative for how to do it. Okay, so let's look at what we call the tree method here, or just trees. So if you have a function of a couple of variables, which are also functions of a couple of variables, and you want to know what the formula is to find the derivative, you'll use a tree. Of a couple of variables. And each of those is also a function of at least one other variable. Then you can use a tree, which you'll see what that is momentarily. To figure out what the formula is for computing the derivative. All right, so how does this work? Well, I'll show you based on the one that we already know. Okay, so this is going to be an example, and then we'll see it for other cases. So suppose z is a function of x and y, and then x is a function of t, and y is also a function of t. Okay, so here's what you would do to figure out this tree. Now, your book does them horizontally, and I've never done them that way. I mean, it doesn't matter. It's just the way you draw them. But I'll draw them right side up. So the way you start figuring out these derivatives, like let's say we want to figure out what dz dt should be, right? We already know it because that was the formula that we had worked out, but we're gonna do this instead. So here's how you start out. So you start out with z as a function of x and y. So you put that here. You go z on top. Now z is a function of x and y. So from z goes to x, z goes to y, right? And then what you do is you say, well, x is a function of t, right? X depends on the variable t. And y also depends on the variable t, like that. So then, if you want to figure out what dz dt is, you basically take every path that goes from z to t, and each line in here is a derivative. Now, when I say each line is a derivative, what do I mean by that? Well, what I mean by that is like this. So from z and x, right? From z to x, you can do a partial derivative. The partial derivative involving the z and the x would be delta z, delta x, right? That's the partial derivative that's between those two. And then from x and t, you could do a partial with respect to x, with respect to t, from the x to the t. Do the same thing for the other side here. So, oops, I don't know what I just wrote the same thing again. Partial of z with respect to y, for there. And then for the one down here, partial of y with respect to t, like that, right? So then what you do is if you think about following every path from that starts at z and ends at t, what we would get is like going this way, you would multiply these two, and you would have, so if we want dz dt, you look at, take all paths starting at z and ending at t, and we add them together. So like you can go from z to x and from x to t. Then if you go from z to x, x to t, the partial derivatives you come across are dz dx, dx dt. So you go partial z with respect to x, partial x with respect to t. And then if you take the other path on the other side, which also goes from z to t, then the partials you pass by are partial z with respect to y, partial y with respect to t. So you go partial z with respect to y, partial y with respect to t. And that's the formula that we had given in that theorem. Okay? Now you might think like, okay, well, what's the point? I don't even see what the point is. So the point is that this method can work out formulas like this even for more complicated scenarios once you understand it. So like, for example, I'm not going to do one. I'm just going to say example. I'm going to say use a tree to work out, let's say, I'm going to do one that's more complicated than we would use for like a first example, just because I think that the more complicated examples are more educational here. So let's say we use a tree to work out, we'll say dz dt again. Yeah. Okay, we'll say dz dt again, but here's what we're going to do. It's going to make more complicated. I'm going to say z is actually going to be a function of x and y and t. Okay, and then I'm going to say that, x. Oh, and by the way, let me just go up here a little bit. Um, Notice that we can say z depends on x, x depends on t, but like the actual names of the functions, like the g and the a, they don't appear in this tree. You don't need them. And usually at some point they kind of stop writing them this way, where they have names like that, and they just say x is x of t. So x is a function of t, and y is a function of t. Now, this might seem like it's the same as the example that we just did, but it's not the same as what we just did because there's this extra t here, right? Well, what's that do? Um, so, do I want to do that? I mean, I guess I do. This is going to be a little bit weird. Um, but I guess we'll do it. Yeah, I don't think I've ever seen this particular example before, so this is just kind of a weird one. But if you were going to do this, you would put the z on top, and then you would just say z has three variables in it, x, y, and t. So you just go x, y, t. That's weird to have there. But then you look further down, you say x is the function of t. So you go t, t, like that. And then each of these lines, remember, is a partial derivative. So you can label them partial z t, partial z y, partial y t, partial x t, partial z x, right? And I'll say it one more time just in case anybody missed it, right? Like the way I'm labeling those is right, like this line goes from the z to the x, so it's z and x. This one goes from x to t, so it's x and t, right? That's how I'm doing these. This one is from z to t, so it's z and t. So if you were going to write this, you have to remember take every path starting at the z and ending at t. So you have to go this way, so there's going to be one formula there. This way, so there's going to be a formula there. And then also this way, a third way to get to a t. And so you have to take all of them there. So if you work it out in this one, it would be dz, dz, dz dt would be partial z with respect to x, right? So I'm going to do this one first. Partial x with respect to t plus z to y. So that's partial z, partial y. Y to t, which is partial y, partial t. And then this extra one that was weird, that's just going to be partial z, partial t. And now it would be weird to have your formula this way, but there's nothing that would stop you from doing that. And also you can see why this derivative is not actually just written this way, because that would be a partial of z with respect to t. That's not the entire derivative with respect to t, because z might have t's in it, but x and y also have t's in it, and we haven't even talked about and so the partial of z with respect to t, it's a small derivative, and it's missing all these parts too. So this is the real derivative of z with respect to t, whereas this is only the partial derivative of z with respect to t, ignoring those other variables that may also be functions of t. So that was a weird example, but let's do another one. So let f be a function of, or let's say, sorry, let z be a function of, let's say, x and y. Let's just do x and y, but this time we're not going to use t's. We're going to do x is actually going to be a function of u and v, and y is also going to be a function of u and v. And in this case, because there's two variables here, this is actually going to be a chain rule when there's two independent variables. That's a new thing. Okay, so we'll just note that this time there are two independent variables, u and v. So there's actually two derivatives you can calculate. You can work out the following. You can work out dz du and, or I'll say or because I said either, at least I started spelling either, dz du or dz dv. Both of those could be worked out. Okay? And so if I say this is what we got, probably the problem asks you for both. So like we would say find the formulas for dz du and dz dv. So there's two of them that you could find now because it's not just a t, this time there's a u and a v. Okay, now you would get them both from the same tree though. So you make your tree, we make the tree exactly the way we did it before. So we put z on top and z has x's and y's. So you go z, x, y. But then x has u and v. So there's two of them this time. And also y is a function of u and v. So it has two, u, v. And so each of those lines, remember, is a partial derivative. So you've got a lot of partial derivatives on here. We've got, what do we got? Partial z, x, partial x, u, partial x, v, partial z, y, partial y, v, partial y, u. Right? So there's a bunch of derivatives here. You don't necessarily use all of them every time. So when we're going to do the formula for dz du, remember what you're looking for is all paths starting at z and ending at u. So we don't care about the ones that end at v. We only care about the ones that end at u right now. So like what would that be? Oh, I can use the highlighter. Hold on. So like you can go from z to x and from x to u. And also you can go from z to y and from y to u. So those are the two paths that start at z and end at u. Okay. And then, well, what would the derivatives be? Well, we can just write them down, right? This is not hard. So from z to x, x to u. So you go dz dx, dx, u, right? And then the other one is simply going to be partial z y, partial y, u. Okay. So those are the two that you would use. Again, it looks like it's correct based on what looks like it cancels, right? The x's look like they cancel, and you have dz du, dz du, dz du. So everything looks like dz du if you canceled it. Okay, so that's one of the ones you need. The other one, oops, would be starting at z and going to v. So from here to here to here, and here, here, right? So that's the ones that start at z and end at v. So it would be dz dv, and that would be partial z x, partial x, v, plus partial z y, partial y, v. And so those would be your two formulas there. And again, they're not that hard to come up with. That's how you do it. Okay, so let's try one of these. Um, we'll try a little bit trickier one. I see one that involves, it looks like a product, or sorry, a quotient rule. So we'll say calculate, um, oh, and they're calling these partials here, sorry, because there are two independent variables, they list those as partials. Let me change this as well then. Okay. Blue, 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 blue. Okay. I think that's all of them. Okay. So let's say calculate, what do we want? Partial z with respect to u and partial z with respect to v. Okay, given, of course, we need functions here. We're going to use um, z is going to be a function of x and y, 2x minus y, x plus 3y. Then x is a function of u and v. It is e to the 2u cosine 3v. And y is e to the 2u sine 3v. Okay, so that's what we got. So you can see from this that you're going to have quite a few partial derivatives to calculate there. Basically, you need the partial derivatives of everything with respect to everything. So, like, we're just going to need these. So, like, we're going to need, let's see, find all these partials that we're going to need. So we need like partial z with respect to x. We need that one. So partial z with respect to x is going to be the derivative of this. I'll write d dx and just move this down. Oops, duplicate it. Duplicate it. So we need that partial, which would need the quotient rule. So the quotient rule would be the bottom times the derivative of the top with respect to x, which is 2, minus the top, 2x minus y, times the derivative of the bottom with respect to x, which is 1, all over the bottom squared. So let me just think about that. Bottom times the derivative of the top minus top times the derivative of the bottom, all over the bottom squared. Yes. Okay, so that's that. You can simplify it a little bit here. What do we got? We got top is, I'm just going to distribute that 2. So we have a 2x plus 6y minus 2x plus y up there. Then x plus 3y squared on the bottom. Combine the x's, you get 0 on top. I'm just 2x, 2x, 6y. So the 2x minus 2x is 0. 6y plus y is 7y. So it looks like 7y over x plus 3y quantity squared. So that's partial z with respect to x. Okay, let's do the same sort of thing for the y. We're going to need that one as well. All right, so same kind of thing. We're going to be doing quotient rule. So bottom times the derivative of the top minus top times the derivative of the bottom, etc. The only difference is this time we're doing our derivative with respect to y. So we have a bottom times the derivative of the top with respect to y. So the derivative of the top with respect to y is -1. And then minus the top, 2x minus y, times the derivative of the bottom with respect to y, which is 3, all over the bottom squared. work that out. I think we can maybe do it in our heads. Probably not. So for x, you have x times -1. So negative x minus 3 times 2x. So 3 times 2x is 6x. So negative x minus 6x. So negative 7x. And then you've got negative 3y minus 3y. So it'd be plus 3y. So negative 3y plus 3y. So it cancels again. Interesting. So I think this is the derivative. Okay. So we've got those partials. Now those weren't the only partials we need. We also need, right? We're also going to need partial x with respect to u, partial x with respect to v, y for u, y for v. So 4 more to do. There's actually 6 partials that we need here. So we need partial y with respect to, I don't know why I'm starting with y. Why would we do that? Partial x with respect to u. Let's do that. So these derivatives are going to be a little easier, right? They look like you might look at this and think, product rule, but no, because remember, when you're doing the partial with respect to u, you treat the v like a constant. So this is all a constant when you're taking the derivative with respect to u. So the derivative of e to the 2u with respect to u is 2e to the 2u. 2e to the 2u, and then just cosine 3v along for the ride as a constant. You also need partial x with respect to v. So same sort of thing. This is a constant now. You're taking the derivative of cosine 3v with respect to v, which will be negative 3 sine 3v. So you get negative 3 e to the 2u sine 3v. Like that. Then we need partial of y with respect to u. So where's y? Here. So when we take the derivative with respect to u, we're just going to carry along the sine 3v. So we only pay attention here. The derivative of e to the 2u is going to be 2e to the 2u again. Sine 3v. And then we also need partial y with respect to v. Same sort of thing. So the derivative of sine 3v is going to be 3 cosine 3v. So we end up with 3 e to the 2u cosine 3v. Like that. Okay. So having done all of that, then what we should be able to do here is combine this all and work out the derivatives that we need. So if we are trying to calculate partial z with respect to u, we'll have this one. So let's just write it out. So let's say use the formulas from the tree. So here's one of them. So we're just going to use that formula from the tree and we just fill in everything. So partial z with respect to x, which is 7y x plus 3y quantity squared times, why am I missing the denominators there? Weird. I didn't get the u. Huh. It's very strange. Okay. Partial z with respect to x, and then partial x with respect to u, which is 2e to the 2u cosine 3v. v. And then plus partial z with respect to y. We're here now. So that is here, partial z with respect to y, which is negative 7x over x plus 3y squared times partial y with respect to u, which is right here, 2e to the 2u sine 3v. Okay. So that is that. We can do the same thing for z and v. Duplicate that, bring it down here. I'm hearing weird noises, guys. Don't know what they are. Okay. All right, so same thing. Um, Now notice that like the dz dx, dz dy shows up in both formulas. So I'm just gonna write those down rather than scroll up for them. So like this was 7y x plus 3y squared something plus I need more room for that something. And then dz dy, which happens to be right here, negative 7x x plus 3y quantity squared. And then we need the other thing. So what do we need? We need dx dv somewhere. Here it is. 3e to the 2u dx dv. Wait. Dx dv is here. Negative 3 e to the 2u sine 3b. Negative. Okay. And then we also need the dy dv, which is right here. So that is 3e to the 2u cosine 3b. Okay. So technically we've done the derivatives, but keep in mind that technically you shouldn't leave it this way because you should have everything in terms of the two independent variables u and v. So, technically you should do this like a third step here. Sub in x equals, what was the x? Basically, you could take these two formulas. Again, you can't see what I'm circling. I remember. Duplicate. You can substitute these things into the above equations. So that instead of x, y, u, and v all together, you would only have only u and v. And that would be an improvement, in theory. Although it'd be a lot of writing, right? So like if I do, like let's say I do partial z with respect to u, let me just copy it, duplicate it. This is what we have. And if you go and you put in your x and your y, that gets pretty complicated right away, right? You have like 7y, which is e to the 2u sine 3b, over x, which is e to the 2u cosine 3b, plus 3y. 3y is e to the 2u sine 3b quantity squared. And then you've got this thing, which should be out to the side. I'll put it up here though. And then you got plus, or minus actually, 7x. X is e to the 2u cosine 3b over, the denominator is the same, so I'll just duplicate it to save myself effort. And you got this term that should be on the end of this. I will take it and just duplicate it and put it right there. I just erased it. Okay, so there's a minus in there. But this is very tedious to do, right? I purposefully picked kind of a long one here, and then I'm not going to do that. I'm not going to do the other partial because it's going to be too long. Okay. So you can do that and then make everything in terms of u and v, but it's kind of like, well, do I have to, right? Are they making me do it? I don't know. So In general, by the way, there is like a pattern to this. Um, so like you can do it without the T if you're careful, because the pattern um, using, I guess, what they call generalized chain rule, which I'm going to write on the board. I'm going to write in the notes, um, just to show you. So imagine you had this. So suppose you had f, and f was just had a bunch of variables. Now, instead of calling them x, y, z, we're just saying a bunch of variables. So like x1, x2, dot, 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 xm. So we're not changing the letter because, there's a finite number of letters there, and I don't know how many x's there are. So you have that. So that's, has m variables, function of m variables, right? And then let's also suppose each of those variables is also a function of more variables. And each xi is actually a function of like a t1 and a t2 and a t3 up to tn. There's no reason that this has to be the same number as this. That's why we use an m here and an n here. Um, so each x is a function of t variables. But n variables, sorry. All right. What we're going to do um, is we have a formula. Sorry, let me change this here. This is supposed to be, move this over. Just say that it's a differentiable function, which, makes sense, right? If it's not differentiable, how are you doing calculating derivatives? But, they say it, we should say it. So what we want is, I want to say what the variable is. So like this, I think they call it what w, by the way. So we can calculate the derivative of w with respect to x, all the x's, and then each of the x's is a function of t. So you could calculate the partial of w with respect to any of the t's. So the formula is this. So they say, partial of w with respect to any of the t's, right? Because I don't know how many t's there are. I see they use a j actually, so I'll use a j. Equals, and I'm going to fill that in a second, but I want to just look at that tree real quick that we would do. So the tree looks like this: w, and then from the w you have like x1, x2, x3, right? That just keeps going though until xn. And then each of the x's is a function of t's, however many t's. Oh, that's an m. In different t's. So this goes t1, t2, dot, 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 tn. And that same thing is for all of these. Oh, man. I was trying to, be sneaky here, but I didn't leave myself enough room to be sneaky. Okay. So, right, each of these has the same thing going on, like that. Okay, so if you wanted the derivative with respect to tj, like let's just draw t1 for example. Like t1 would be from w to x1, from x1 to t1, but also w to x2, x2 to t1. And then, you keep doing that until you go w to xm, xm to t1, right? I'll just delete that one. So there's a lot of different ways to get from w to t1, but they're all like this, right? Like this first one that I drew was w to x1, and then x1 to t1. And then the next one is w to x2, and then x2 to t1. And you just keep doing that down the line until you finally get w to xm, and then xm to t1. Now, the only thing I did wrong here was I said, let's just imagine we're doing that for 1. So you'd have this long derivative for t1, but we were supposed to be doing it for tj. So actually, all those t1s should have been tj's. Rewrite those j's there so they look more like j's. Okay. So that's what's going on there. And so you can get it from the tree, but also they write this as a formula, just like a generic formula, but it's just using that tree. And so they call that the formula that's called the generalized chain rule, because we just wrote it out, right? For whatever, like however many variables you have, this is the chain rule. Hey, why'd you do that? Go there, go to the end. Now stop. Okay. All right. So that is the generalized chain rule. It's right up there. And it's fine. We drew some of these tree diagrams already. We're not going to do another one. Okay. Let's do implicit differentiation. Okay. So here's the thing, maybe. So this is just kind of an idea here to show you where these formulas are coming from, but you're not going to do this, okay? So this is just kind of like where the formulas I'm going to give you come from. And this is just the idea of it. Okay, so suppose we have this function. So suppose we have z equals f of x comma y. All right. And what we want is like a dy dx, but you can't just find dy dx. You got to, so that's a little bit, okay. So they say, suppose z equals f of xy defines y as a function of x implicitly. Now that's a little bit, I don't like the way that they're writing that, because like they're saying, like obviously there's x's and y's in here, right? But it says it defines y as a function of x, but what about the z? And then they say y is a function of x implicitly, they say via the equation f of xy equals 0. Now, okay, yeah, if you put a 0 in for z, there's no z, and now everything is in terms of x's and y's, and that makes sense. But like, they're not justifying why you would do that. And this does not, like, z equals f of xy does not define y as a function of x implicitly. You have to do this first, and then it does. So I don't like the way that they're wording this here. A little bit wrong or weird. But that's the scenario that they gave you, okay? So they say defines y as a function of x implicitly via the equation f of xy equals 0. And what we want to do is I want to find, for example, dy dx. So that's the game. We want to find dy dx. What is dy dx? Okay, and so since they mention implicit here, we are going to be doing, this is going to be implicit differentiation. Okay, and how are we going to do it though? So let's start with what we have here. We don't have really a lot of good places to get started. So let's start with f of xy equals 0. So start here. F of xy equals 0. You have to do that. You can't start with z equals f of xy because, again, that doesn't actually define y as a function of x because of the z's involved. But if you put a 0 in for z, now there's no x. Now everything's x or y. Okay, so start here. Now we're trying to find dy dx. So let's take the derivative with respect to x. So you have the derivative with respect to x of f of xy equals the derivative with respect to x of 0. Now, okay. This is this is a little bit dumb, maybe. The tree here looks like this. So you have f on top. F is a function of x and a function of y, right? That's what, right? F is a function of x and y. It says it right here. But we also said up here that we were going to be treating y as a function of x. So y is a function of x. So you come up here on your tree and you can say, well, y is also a function of x. So that's a weird looking tree, but this is what we have. And that would tell you how to calculate these derivatives because you take every path from f to x. So this is partial f x, this is partial f y, and this is partial y x. Okay, which is actually not even partial, but anyway, let's just do this. So if you were going to take this derivative here, the derivative with respect to x of f of xy, you use your tree here, and so you get two terms. First term is going to be f to x is partial f with respect to x. And then you have this one to go from here to here, partial f with respect to y. And then partial y with respect to x. And something they do in your book is they say, like, they don't even say it actually, they just write it. But what they're saying is this only has x's, y's, and we're assuming y is a function of x. And since y is a function of a single variable x, we don't really need to call this the partial anymore. So instead of calling it the partial, they just call it the regular dy dx derivative. Because y is a function of x, they don't need, there's no other variables involved, so we don't have to call it a partial derivative. It's just the derivative. All right, on the other side, the derivative of x is 0. So they get this equation here. And then if you were trying to find dy dx, remember that was the question here, what is dy dx? You would then solve for dy dx with algebra. So solve for dy dx with algebra. And that's not that hard. You would take the df dx over to the other side. So you'd have partial f partial y dy dx equals negative partial f partial x. And then if we're trying to solve for dy dx, then we need to divide this df dy term over to the other side, and you get dy dx is negative partial f partial x over df dy. And then that's like a formula. Okay. And so, yeah. So then they got this theorem, which actually, maybe I just, oops, that's not what I wanted. I was going to say maybe I'm going to be so lazy, I'm just going to copy paste this um, thing rather than writing it out. Yep, that's what we're doing. We're just cheating. Done. Save to photos. Go here. Added lag. Photo library. I'm probably going to have to do this twice. Okay. Come on, let me drag the thing. All right. So there's the formula for implicit differentiation here of two or more variables. And yeah, so the formula we just calculated is right. This one right here is just this one right here. And in this scenario, and this is like, this was if, hold on. This is if z is a function of x and y, um, then this is the only dy dx you can calculate. They say provided fy is not zero because that's in the denominator. So obviously you can't divide by zero. And then down here, if you have a function of x, y, and z, then there's two partial derivatives you could do. Well, more than two partial derivatives you could do, but you could do partial z with respect to x, or you could do partial z with respect to y, and these are formulas. And you'd get these formulas exactly the way that we got this one, which is to say you'd have to make a tree like this. So like if you wanted to, if you were trying to derive those formulas that are called 4.35 there, you would have like the z is x, y, uh, wait, oh, oops, sorry. F is x, y, z. And then if you were trying to find dz dx or dz dy, then in principle, like the x could be a function of y. Uh, really? Hold on. Z is a differentiable function of y and x. Hold on a second. What would you need there? You'd have f is a function of x, y, and z, but then what do we do up here? Z is a function of x and y. Okay, so you'd have like this. Okay, that's what they say. So if you were trying to do, if you're trying to come up with the derivative for dz dx, then you would have like, um, then you would have what would you have? What did we do first? Okay, we just did that derivative from f to x. Okay, so yeah, so if you were trying to find the dz dx there, you would go f to x, and then f to z to x. And after you do the same exact thing that we did in the work up here, then you would just get this formula, which, worked out the same as that formula. But again, we're not going to actually work those out. Even just drawing as much as I drew was already too much effort. Um, but what we will do is actually use this formula for implicit differentiation to actually calculate some derivatives. So we can practice that. Okay, so let's try this. Let's try these. So this is implicit differentiation examples here, which is our last topic. Should be fine. All right. So we'll do two of these. We're going to go find dy dx if y is defined implicitly by 3x squared minus 2xy plus y squared plus 4x minus 6y minus 11 equals 0. Now, by the way, just a comment here. You could find dy dx using calculus 1 or calculus 2, I guess, depending on which class you're in, style implicit differentiation. So you can do this in Calc 1 or 2 with implicit differentiation. But we're going to use the formula that we derived in this class, which is new. Okay, so I'm not going to do it that way. I'm going to use the formula that we had. So for us, you have to make sure you understand what is what here. So in order to use this formula here, you have to understand that, first of all, they're talking about an f here, right? They're talking about this f. What's f? Well, they say that the equation is f of xy equals 0. So from that right there, that tells you that whatever equation they give you, even if it's not called f, you have to call it f in order to use this formula. So back down here, then this must be f. 3x squared minus 2xy plus y squared plus 4x minus 6y minus 11. That's the f. Okay? And then having written that down, we know our formula, which I'm looking it up here, is negative df dx over df dy. So we know the formula is this. Also, just kind of a side note here. Remember on the previous examples, and one thing I did fairly often was I said like if you're calculating dw dt, like you can think of those canceling. You have like dw dt, and I said that you can't really cancel that way, but it helps give you the idea of what's going on. The same thing is still true down here because take a look at this, right? Like if I just take this, actually, hold on. If I just take this, duplicate, stop, why, work. Okay. If you just pretended that these were actual fractions, for example, for a minute, then you would have like df dx times the reciprocal of this, which would be dy df, and then like somehow these would cancel and you'd have like dy dx. Now you might say like, okay, well that's dy dx. Okay, sure. But why is it negative? Well, it's negative because we calculated it and it was negative. So, again, it breaks down, the idea breaks down, right? You can't actually cancel those. It's not actually the formula. But if you pretended for a minute, like dy dx and dy dx, so it kind of makes sense that it's the x derivative on top and the y derivative on the bottom. Sort of feels like it makes sense, even though that's not like technically valid math. Anyway, the formula is what we just wrote down. So you only have two little derivatives to calculate. They shouldn't be hard. So we need df dx, which is the derivative of this function with respect to x. So what is it? So the derivative of 3x squared is 6x. The derivative of negative 2xy with respect to x is minus 2y. This only has y's. The derivative of 4x is going to be 4. And actually nothing else has an x. So that's done. The other partial derivative we need is partial f with respect to y. So let me just say partial derivatives here. Okay, so that's what we're doing. We're calculating the derivative of f with respect to y, just as easy. So derivative of negative 2xy is going to be negative 2x this time. Here's a y. Derivative of y squared is 2y. Here's another y. Derivative of negative 6y is negative 6, like that. And we're done. And then once you have those two partials, then we can, write out the formula. So you need to know to look up that formula. And so the dy dx is, according to our formula, it's just negative, and then you put the x derivative on top and the y derivative on the bottom. So x derivative on top, so it's 6x minus 2y plus 4, negative, and then on the bottom, the y derivative, negative 2x plus 2y minus 6. And you can simplify this however you want, depending on how much effort you want to put into this, right? Like you can factor a 2 out of everything, and you can multiply the negative in. So you would have, like, if you cancel a 2 on top and bottom, then you'd have, if you cancel the 2 on the top and the bottom and multiplied in the negative, you would have negative 3x plus y minus 2. And then on the bottom, just minus x plus y minus 3, I guess. So I tried to put in the negative on top and also cancel a 2 at the same time. And there you go. But that was not hard, right? Like this should have been, technically easier than anything we've done up till now. Let's do one more of these, and then we will be done for the day. So find partial z, partial x, and partial z, partial y, given x squared e to the y minus y z. Oh, you got me with the z there. E to the x equals 0. Okay. Wait. No, that's fine, actually. Okay. Okay, that's fine, I think. Okay. Sorry. I was just thinking if I was going to have to rearrange this formula here. All right. So how do we do this? So first of all, you need to make sure you understand the f again. So this whole thing is f. So f of x, y, z is x squared e to the y minus yz e to the x. Okay. And our first step actually is we're going to be calculating some of these derivatives, right? Well, which derivatives do we need? Well, if we're going to find the dz dx and the dz dy, we're going to need all of the ones listed here. So there's 4 of them, right? df dx, df dy, df dz. Okay, 3 of them. df dx, df dy, and df dz. So we're going to need 3 partials, which makes sense. There's 3 variables here. And then we can use our formulas. So partial f with respect to x. So remember, every other variable is a constant. So when we take the derivative of f with respect to x, we're just looking at this derivative is going to be 2x e to the y. 2x e to the y. And here, when we take the derivative with respect to x, the derivative of e to the x is e to the x. So yz e to the x. Easy. Partial f with respect to y. So derivative of e to the y is e to the y. So we're going to have x squared e to the y minus, here there's only one y right there. The derivative of y is 1. So this is going to be a 1, and then z e to the x. And then we need the partial f with respect to z. And so there's only one z here. So this derivative is going to be 0, and this derivative, the derivative of z is going to be 1, and we're going to have negative y e to the x, which is negative y e to the x. So those 3 partials are pretty easy, right? So compute your partials. that you're going to need. And then we're going to use our formulas. And the formulas, I think they're exactly the same as the formula we used, right? So like when you're doing zx, then actually over here, it's the x derivative on top and the z derivative on the bottom. And also there's the negative sign. And when you do dz dy, again, if the y is on the bottom here, it's on the top here. And then z's on top on the left, z's on the bottom on the right. And also there's a negative. So you can, there's kind of clues here to help you remember these things. So if we're doing, where are we, partial z with respect to x, so we can use the formulas. So if we're doing partial z with respect to x, again, the formula, right? Try to remember it. X is on bottom here, so it'll be on top here. So negative df dx over df dz, right? That was the formula. So simply fill it in. So negative, the x derivative is 2x e to the y minus yz e to the x. And the df dz derivative is negative y e to the x. Which, having done that, I can just cancel those negatives I see. We'll just cancel those. Okay, that's pretty straightforward. The other one we want is partial z with respect to y, which will be negative partial f y on top, and then f z on the bottom. So we just did the bottom, so I'll recopy it. And the df dy derivative is x squared, negative out front, e to the y minus z to the x. Okay. Again, you can cancel those negatives. So very straightforward, right? And that's how implicit differentiation works for these kinds of functions. Again, the actually what we did on the first problem, right? This one up here, really you could have calculated that with regular implicit differentiation in Calc 1. So this is just kind of an improved method where we kind of wrote out what the final formula is, and then we just have to, I don't know, save some work. You couldn't do this in Calculus 1 or 2 because you didn't know what partial derivatives were at that time. So you couldn't use this kind of theorem. Okay. So I think that's it for now. These really are straightforward, and I think you will have an okay time with them. Just a lot of formulas to keep straight. Anyway, that's it for now. I will talk to you guys later.